Every diagram you have ever seen of the solar system is a lie. Not a small distortion, a fundamental one. Those flat pictures with planets lined up around the sun hide something enormous. They erase two entire directions. Directly above the sun and directly below it, the universe does not end. It opens. But into what? That question sounds childishly simple until you try to answer it. Because in space, there is no universal up or down. The direction you call above depends on which plane you choose, and the solar system's plane is tilted 60 degrees from the galaxy's plane. What sits over our star's head in one frame is completely different cosmic territory in the other. The real geometry is far stranger than any classroom poster ever suggested. If you enjoy having your picture of the universe quietly dismantled and rebuilt from scratch, a like and a subscribe genuinely help this channel keep making these deep dives. It costs nothing and it means the world. Now, get yourself comfortable. Let's begin. Close your eyes and picture the solar system. You already know what you see. The sun sits in the center, bright and dominant. The planets stretch outward in a clean line, each one smaller than the last, each one farther from the warmth. Maybe you imagine the orbits as circles, maybe as ellipses if your science teacher was particularly strict. Either way, you see a flat picture, a disk, a diagram drawn on a page or projected on a screen, with everything arranged left to right or in a tidy ring. You have seen this image 1,000 times. On posters, in textbooks, in documentaries, in animations that zoom through the planets one by one. It is the single most reproduced picture in all of science education, and it is hiding something so fundamental that once you see it, you cannot unsee it. That picture has no up, it has no down. Every version of the solar system you have ever encountered presents the planets as though they exist on a tabletop. The diagram extends outward in two dimensions, left and right, near and far, but it never asks you to look above the table. It never asks you to look below it. Those two directions, the ones that point straight up from the sun and straight down from it, are simply erased, deleted from the image, treated as though they contain nothing worth showing. And here is where it starts to get strange. If you ask most people what lies directly above the sun, they would pause. They would hesitate. Not because the question is hard in the usual sense, but because their mental picture of space has no room for it. The flat diagram is so deeply embedded in how we imagine the solar system that the vertical directions feel like they do not exist. Above the sun feels like asking what is north of the color blue. The question seems to point at nothing, but it does point at something. It points at real, physical, three-dimensional space that extends in every direction from our star, including the two directions that every diagram has trained you to forget. Before we can answer what lies above and below the sun, we need to confront an uncomfortable truth about direction in space. There is no universal up. There is no universal down. On Earth, we take these directions for granted. Down is toward the ground. Up is toward the sky. Gravity defines the axis, and every human being on the planet shares the same instinctive understanding of which way is which. But leave Earth, leave its gravitational field, and those words lose all meaning. An astronaut floating in open space has no down. Every direction looks the same. The universe does not come with a built-in floor. This is not just a poetic observation. It is a geometric fact that determines everything about how we describe the space around the sun. When someone asks what is above the sun, the first thing a scientist has to do is ask a question in return. Above relative to what? Because in the emptiness of space, above only means something if you first choose a reference plane, a flat surface that defines the horizon, the way the ground defines up and down on Earth. Pick a different reference plane, and above points in a completely different direction. The answer to the question changes entirely depending on which plane you choose. And this is where the solar system gives us our first natural reference. The planets do not orbit the sun in random directions. They all orbit in roughly the same plane, like marbles rolling around the rim of a shallow bowl. This shared orbital plane is called the ecliptic, technically defined as the plane of Earth's orbit around the sun, but it closely matches the general plane in which all the major planets travel. The ecliptic is the solar system's own built-in floor. It is the reason the flat diagram exists in the first place. When you see that poster of the planet stretched out in a line, you are looking at the ecliptic edge-on, but calling it a plane makes it sound more precise than it really is. The ecliptic is a mathematical surface, not a physical wall. Nothing stops objects from drifting above or below it. And in fact, the planets are not perfectly confined to the ecliptic at all. Earth's orbit defines the plane exactly, by definition, but Mercury's orbit is tilted about 7 degrees from it. Venus is tilted about 3.4 degrees, Mars about 1.8, Jupiter only 1.3 degrees, Saturn 2.5 degrees. These are small angles. The major planets stay close to the ecliptic, which is why the flat diagram works as a rough approximation, but go further out and things get messier. The dwarf planet Pluto orbits at an inclination of over 17 degrees to the ecliptic. Some Kuiper belt objects have inclinations of 30 degrees or more. Comets arriving from the outer solar system come in from every direction. Their orbits tilted at wild angles that have no respect for the ecliptic whatsoever. The solar system is not a perfectly flat disk. It is a roughly flat disk with a lot of stragglers drifting above and below the main plane. Still, the ecliptic gives us our first useful definition of above and below. If you stand on the ecliptic plane and look straight up, perpendicular to the disk of the solar system, you are looking toward what astronomers call the north ecliptic pole. This is a specific direction in space. It points toward the constellation Draco, the dragon, a winding pattern of stars in the northern sky. If you look straight down from the ecliptic, perpendicular in the opposite direction, you are looking toward the south ecliptic pole, which points toward the constellation Dorado, deep in the southern hemisphere sky. These are real directions. They are not arbitrary. They are defined by the geometry of the solar system itself, and they let us finally ask the question with precision: what lies directly above the Sun, perpendicular to the ecliptic, toward the north ecliptic pole in Draco? The answer is startling in its emptiness. Within the immediate solar system, almost nothing lies in that direction. Think about everything you know that orbits the Sun, the 8 planets, their moons. The asteroid belt between Mars and Jupiter, containing millions of rocky objects, the Kuiper belt beyond Neptune, home to Pluto, and thousands of icy worlds, the scattered disk of distant frozen bodies. All of these objects are concentrated near the ecliptic. They hug the solar system's flat plane like cars on a highway. If you leave the highway and drive straight up, perpendicular to the road, you leave behind almost everything the solar system contains within the first few degrees of elevation. Picture it this way. Imagine shrinking the entire solar system so that Neptune's orbit fits on a dinner plate. All 8 planets, the asteroid belt, and most of the Kuiper belt would be confined to that plate, a thin layer of material spread across its surface. Now look at the space directly above the plate. Hold your hand a few inches over the center. In real terms, your hand is hovering in a region of the solar system that contains essentially nothing. No planets, no asteroids, no Kuiper belt objects. Just the thin haze of the solar wind streaming outward from the sun's poles and the near-perfect vacuum of interplanetary space. The solar system is astonishingly flat when you actually examine its 3-dimensional structure. Almost all of its interesting contents are crammed into a thin disk, and the directions perpendicular to that disk are staggeringly barren. This emptiness is not gradual, it is dramatic. Along the ecliptic plane, the solar system is rich with objects spread over billions of miles, but perpendicular to the ecliptic, you escape the zone of significant material within a tiny fraction of that distance. It is as though the solar system has been stamped out of sheet metal, all surface, almost no thickness. The contrast between the busy horizontal and the vacant vertical is one of the most striking features of our cosmic neighborhood, and it is completely invisible in every flat diagram you have ever seen, because those diagrams never show you the vertical dimension at all. Now travel farther. Leave the solar system entirely and keep heading toward the north ecliptic pole, straight up from the sun's orbital plane. What do you encounter? Stars. But not for a while. The nearest star to our Sun is Proxima Centauri, at a distance of about 4.24 light-years. But Proxima Centauri does not sit directly above the ecliptic. It sits at an angle, somewhere off to the side in 3-dimensional space. The stellar neighbourhood around the Sun is not organised along the ecliptic. Stars are scattered in all directions, roughly uniformly, with no preference for the solar system's plane. The ecliptic means nothing to other stars. It is a purely local feature, relevant only to the family of objects orbiting our Sun. So if you travel directly above the Sun in the ecliptic frame, you pass through empty interplanetary space, leave the solar system's disk of material behind almost immediately, and then drift for light years through the interstellar medium, the thin gas and dust between stars, before you encounter another stellar system. And that system will have its own orbital plane, tilted at some random angle completely unrelated to ours. The ecliptic is not a cosmic feature. It is a household quirk of our particular planetary family. This leads to an unsettling realization. The flat diagram has trained us to think of the solar system as fundamentally two-dimensional, a disk with a center and an edge. But real space has 3 dimensions, and 2 of them, the ones pointing above and below the ecliptic, are essentially abandoned by the solar system's contents. We live on a flat structure floating in a 3-dimensional void, and the void above and below is deep, incomprehensibly deep. It extends forever in both directions, thinly populated by distant stars that have no connection to our ecliptic whatsoever. But we are not done, because the ecliptic is only the first reference plane, and it is not even the most natural one for talking about what is above the Sun. The Sun itself is a rotating body. It spins on its own axis, and because it is a sphere of plasma rather than solid rock, different latitudes rotate at different speeds. This rotation still defines the Sun's own equatorial plane, and it defines the Sun's own north and south poles. The Sun's north pole is not the same as the ecliptic north pole. The Sun's rotational axis is tilted several degrees relative to the ecliptic. That means if you draw a line straight up from the Sun's north pole and another straight up from the ecliptic north pole, those lines diverge. They point in slightly different directions. They are close, but they are not the same. This tilt might sound trivial. 7 degrees is not much, but it creates an important conceptual distinction. When you ask what is above the Sun, do you mean above the orbital plane of the planets, or above the Sun's own rotational pole? The 2 answers are slightly different, and the distinction matters because it reveals something deeper. Even within the solar system, there is no single, universally agreed upon direction for above. The ecliptic says one thing. The Sun's spin axis says another. Both are legitimate reference frames. Both are physically meaningful. And they disagree by 7 degrees. And there is a third frame hiding between those 2 that most people have never heard of. The ecliptic is defined by Earth's orbit. It is a convenient reference because we live on Earth, and our measurements of everything else in the solar system are made from here. But Earth is not the most important planet gravitationally. Jupiter is. Jupiter contains more mass than all the other planets combined, roughly 318 times the mass of Earth. Its gravitational influence dominates the dynamics of the entire solar system. When a comet falls inward from the Oort Cloud, it is Jupiter that most often deflects it. When a small asteroid drifts too close, it is Jupiter's gravity that kicks it into a new orbit, or flings it out of the solar system entirely. Jupiter is the gravitational king, and its orbit does not align perfectly with Earth's. This matters because the most physically fundamental plane of the solar system is not the ecliptic. It is something called the invariable plane. The invariable plane is defined by the total angular momentum of the entire solar system, the combined rotational momentum of every planet, moon, asteroid, and grain of dust orbiting the Sun. Angular momentum is a quantity that the solar system conserves. It does not change over time unless an outside force acts on the system. The invariable plane, therefore, represents the true dynamical midplane of the solar system, the plane around which everything is actually organized when you account for all the masses and all the motions at once. Because Jupiter dominates the solar system's angular momentum budget, contributing roughly 60% of the total, the invariable plane is tilted toward Jupiter's orbital plane and away from Earth's. The angle between the ecliptic and the invariable plane is about 1.6 degrees. That is small. Smaller than the tilt between the ecliptic and the Sun's equator. But it is real, and it introduces a subtle but important point. The plane that every textbook treats as the solar system's floor, the ecliptic, is not actually the most fundamental plane of the system. It is Earth's plane. The system's true dynamical plane is slightly different, tilted by Jupiter's gravitational dominance. If you define above as perpendicular to the invariable plane, rather than perpendicular to the ecliptic, you get a third version of vertical within the solar system. The invariable plane's north pole points in a slightly different direction from the ecliptic north pole, which already points in a slightly different direction from the Sun's rotational north pole. 3 planes, 3 definitions of up, 3 different directions, all within the same local system of one star and its planets, and none of them is more correct than the others. The ecliptic is conventional. The Sun's equator is physical. The invariable plane is dynamical. Each one captures a different truth about the solar system's geometry, and each one draws a slightly different line through the Sun pointing toward a slightly different patch of sky. We have not even left the solar system, and the direction called above has already fractured into 3 competing answers. The flat diagram picked one of these answers, the ecliptic, and presented it as though it were the only one. It never mentioned that Jupiter quietly defines a different flaw, or that the Sun's own rotation defines yet another. The diagram's version of up was always just one choice among several, a choice so deeply embedded in how we teach astronomy that most people never realize a choice was made at all. This disagreement gets dramatically worse when you zoom out. The Sun does not just sit in the middle of a family of planets, it belongs to a galaxy. The Milky Way is a vast disk of roughly 400 billion stars, and it has its own plane, its own equator, its own north and south poles. The Sun orbits the center of this galaxy at a distance of about 26,000 light-years, traveling at roughly 230 kilometers per second, completing one full orbit in approximately 230 million years. Here is where the geometry becomes truly disorienting. The ecliptic, the solar system's orbital plane, is tilted about 60 degrees relative to the galactic plane. 60 degrees, not 6. Not 16, 60. The solar system does not sit neatly inside the Milky Way's disk like a coin lying flat on a table. It is tilted at a steep angle, like a coin jammed into the table on its edge, and then leaned over. If you could somehow see both planes at once, the ecliptic and the galactic plane, they would cross each other at a sharp angle that looks almost perpendicular. This means that the direction called above in the solar system's frame, straight up from the ecliptic toward Draco, is almost sideways in the galaxy's frame. And the direction called above in the galaxy's frame, straight up from the galactic disk toward the constellation Coma Berenices, points in a completely different direction from the ecliptic North Pole. The 2 versions of up are separated by 60 degrees. They are not even close to the same direction. Let that sink in. When you picture the solar system as a flat disk and imagine looking straight up from it, you are not looking up in galactic terms. You are looking diagonally through the galaxy, at a steep slant to the Milky Way's disk. And when the galaxy defines its own up, pointing straight out of the galactic plane, that direction cuts through the solar system's ecliptic at a dramatic angle, passing through what the ecliptic frame would call a direction far from vertical. The 2 reference planes do not just disagree. They are rotated so far from each other that they define almost completely different vertical axes. Above the Sun in solar system terms and above the Sun in galactic terms are 2 different cosmic neighborhoods. They contain different structures, they lead to different destinations, they open into different depths of the universe, and most people have never even considered that there might be 2 competing definitions, because every diagram they have ever seen uses only one reference plane and never mentions the other. This is the first real fracture in the flat picture. The diagram on the classroom wall does not just oversimplify the solar system. It imposes a reference frame without telling you it is doing so. It picks the ecliptic as the flaw and pretends that the resulting version of up and down is the only one that exists. But the galaxy has its own flaw, tilted 60 degrees away, and that flaw defines a completely different set of directions. The Sun sits at the intersection of these 2 planes, embedded in one, orbiting within the other, its own spin axis tilted slightly from both. What seemed like a simple question, what is above and below the Sun, has already fractured into at least 3 different questions depending on which axis you choose. The ecliptic, the Sun's rotation, and the galactic plane each draw a different line through the Sun, and each one points above toward a different region of space. The flat diagram cannot show you this. It was never designed to. It was designed to show planetary orbits, and for that purpose it works fine. But it has a side effect that nobody talks about. It teaches your brain to think of the sun as living in a two-dimensional world, a disk with an edge, a map with a border, and it quietly erases the third dimension, the dimension where the real complexity of the sun's cosmic position reveals itself. The moment you add that third dimension back, the moment you ask what is above and below, the clean, flat picture shatters and something far stranger takes its place. Every flat diagram you have ever trusted was not wrong about the orbits. It was wrong about the universe. It showed you the floor and forgot to mention the ceiling, the basement, and the fact that the building is tilted 60 degrees sideways inside a much larger structure that has its own architecture entirely. We have only scratched the surface. The ecliptic frame showed us emptiness above the sun, a barren vertical escape from the busy disk of planets. But we have not yet explored what the sun's own poles reveal about its immediate three-dimensional environment, or what happens when you follow the solar wind straight up from the sun's north pole into the interstellar medium beyond. The solar system's local neighborhood has hidden vertical structure that most people never learn about, including a vast cavity in the gas between the stars that surrounds the sun on all sides like a cocoon. That structure has a shape, and that shape is not a sphere. It is stretched above and below in a way that connects directly to the galactic plane and the directions we have not yet explored. The ecliptic was only the first layer. The next layer sits closer to the sun itself, defined by its own spin, its own wind, and the strange three-dimensional bubble it has blown into the space around it. And when you see what that bubble looks like from above, the flat picture breaks apart even further. So far, we have looked straight up from the ecliptic, the orbital plane of the planets, and found almost nothing. The solar system's contents are crammed into a thin disk, and the directions above and below that disk are staggeringly empty. But the ecliptic is not the sun's own frame of reference. The sun has its own body, its own rotation, its own axis, and its own poles. And when you shift from asking what is above the solar system's orbital plane to asking what is above the sun itself, above its north pole, the story changes in ways most people never expect. The sun rotates. This seems obvious once you hear it, but many people never think about it. They picture the sun as a stationary ball of fire sitting at the center of the solar system while everything else moves around it. In reality, the sun spins on its axis, completing one full rotation roughly every 25 days at its equator. Near its poles, where the surface moves more slowly because the sun is not a solid body but a churning sphere of plasma, the rotation period stretches to about 34 days. This differential rotation, the equator spinning faster than the poles, is one of the forces driving the sun's complex magnetic field, tangling and twisting magnetic field lines until they snap and reconnect in violent eruptions we see as solar flares and coronal mass ejections. The sun's rotation defines a north pole and a south pole, just as Earth's rotation defines ours. The sun's north pole currently points toward a spot in the sky near the constellation Draco, close to but not exactly aligned with the ecliptic north pole. The offset is about 7.25 degrees. That might sound minor, and in everyday terms it is, but it establishes a critical principle. The sun's own vertical axis is not the same as the solar system's orbital axis. Even here, at the very center of our planetary family, up has more than one meaning. What makes the sun's poles genuinely different from the ecliptic poles is what they do to the space around them. The sun is not just a glowing ball, it is a machine that actively shapes its environment. Every second, the sun blasts roughly 1 million tons of charged particles outward in all directions. This stream of protons, electrons, and heavier ions is called the solar wind, and it fills the entire solar system, rushing outward at hundreds of kilometers per second until it finally slams into the interstellar medium and can push no farther. The bubble inflated by this wind, the region of space dominated by the sun's outflow, is called the heliosphere. And the heliosphere is not a simple sphere. Here is where the sun's poles become fascinating. The solar wind does not blow evenly in all directions. Near the sun's equator, the wind is slower and denser, tangled by complex magnetic field structures. Near the poles, the wind is faster and thinner, streaming outward in a cleaner, more uniform flow. The difference is significant. Equatorial solar wind typically moves at roughly 400 kilometers per second. Polar solar wind screams outward at 700 to 800 kilometers per second, nearly twice as fast. We know this because of a spacecraft called Ulysses. Launched in 1990, Ulysses was designed to do something no other probe had done before. It flew to Jupiter, used the giant planet's gravity to fling itself out of the ecliptic plane, and then swung into an orbit that carried it over the Sun's north and south poles. For the first time in history, a human-made object looked down on the Sun from above and below. What Ulysses found confirmed theoretical predictions, but still surprised scientists with its clarity. The solar wind over the poles was strikingly different from the wind along the ecliptic. It was faster, steadier, and less turbulent. The polar regions of the heliosphere are being inflated by a fiercer, more uniform gust of particles than the equatorial regions. The reason the polar wind is so different comes down to what the Sun's poles actually look like. If you could photograph the Sun from directly above its north pole, the view would be strikingly unfamiliar. The bright, mottled surface that we see from Earth, covered in sunspots and active regions along the equatorial belt, gives way near the poles to something darker and calmer. Vast regions of the Sun's outer atmosphere, the corona, appear as dark patches in ultraviolet and X-ray images. These are called coronal holes. They are not holes in the physical surface. They are regions where the Sun's magnetic field, instead of arching back down to the surface in closed loops, opens outward into space, like the flared end of a trumpet. Along those open field lines, plasma streams freely outward without being trapped, producing the fast, steady solar wind that Ulysses measured over the poles. During periods of low solar activity, a single enormous coronal hole can cover the entire polar cap, making the top of the Sun look like a dark well surrounded by the brighter glow of the equatorial corona. The Sun literally looks different from above than it does from the side. The face it shows Earth, viewed from within the ecliptic, is not the same face it presents to the universe above and below its poles. This means that if you could somehow hover directly above the Sun's north pole and look down, you would be sitting in a stream of solar wind moving nearly twice as fast as the wind bathing Earth. You would be in a cleaner, less chaotic magnetic environment. And you would be looking down at the Sun from a perspective that no planet ever sees, because all the planets orbit near the Sun's equator, trapped in the ecliptic, experiencing only the slower, messier equatorial wind. The view from above the Sun is not just geometrically different from the view along the ecliptic, it is physically different. The environment itself changes when you leave the plane of the planets and move overhead. Now follow that polar solar wind outward. It streams away from the Sun's north pole at 800 kilometers per second, racing into interplanetary space. It passes through a region where no planets orbit, where nothing interrupts its flow for billions of miles. Eventually, after traveling roughly 100 astronomical units from the Sun, give or take, the solar wind hits a boundary. It has been pushing against the thin gas of the interstellar medium, the material between the stars, and at this distance, the two pressures balance. The solar wind slows abruptly at a boundary called the termination shock, piles up in a turbulent region called the heliosheath, and finally reaches the heliopause, the outer edge of the Sun's domain. Beyond the heliopause, interstellar space begins. We have directly measured this boundary, but only along the ecliptic. The Voyager 1 and Voyager 2 spacecraft both crossed the heliopause, Voyager 1 in 2012 and Voyager 2 in 2018. They confirmed that the heliosphere has a definite edge and that interstellar space beyond it is real, measurable, and different from the space inside. The interstellar medium is denser, colder, and threaded with a galactic magnetic field that has nothing to do with the Sun. But neither Voyager flew over the Sun's poles. Both travelled roughly along the ecliptic plane, exiting through the sides of the heliosphere. The shape of the heliosphere above and below the Sun's poles remains less directly measured. Models suggest the heliosphere is not a perfect sphere. It is compressed on the side facing the direction of the Sun's motion through the interstellar medium and elongated on the trailing side, somewhat like an egg or a teardrop. Over the poles, the heliosphere may extend slightly farther than along the equator, because the faster polar wind pushes harder against the interstellar medium. but the exact shape above and below remains an active area of research, constrained more by models than by direct observation. The shape of the heliosphere is one of the most actively debated questions in heliophysics, and it bears directly on the question of what lies above and below the Sun. For decades, the standard model depicted the heliosphere as a comet-shaped structure, with a blunt nose facing the direction of the Sun's motion through the interstellar medium and a long tail trailing behind, stretched by the oncoming flow of interstellar gas the way a windsock stretches in a breeze. In this model, the heliosphere above and below the Sun's poles would be roughly symmetric, bulging slightly outward because of the faster polar solar wind, but otherwise forming a smooth, rounded surface. Then in 2020, a team led by Merav Ofer at Boston University proposed a radically different geometry. Using magnetohydrodynamic simulations, they argued that the heliosphere might not have a long tail at all. Instead, it could be shaped more like a croissant, a compact, rounded structure with two short jets of material trailing off the back, one above the ecliptic and one below. In this model, the heliosphere is much smaller than the comet picture suggested, and its shape above and below the Sun's poles is dramatically different. The polar regions become part of the jets rather than part of a smooth dome. The boundary between the Sun's domain and interstellar space curves inward more tightly over the poles, and the transition from solar wind to interstellar medium happens at a different distance depending on whether you travel above the pole or along the equator. The debate is not settled. Both models make predictions about what conditions should look like at the heliosphere's boundaries, but we have only measured those conditions along two paths: the trajectories of Voyager 1 and Voyager 2, both of which travelled roughly along the ecliptic. Neither probe went over the poles, neither sampled the heliosphere's shape in the vertical direction. The Interstellar Mapping and Acceleration Probe, a NASA mission built to map the heliosphere's three-dimensional structure by detecting energetic neutral atoms streaming inward from the boundary, should help resolve the debate significantly once its observations begin arriving over the coming years. What matters for our question is the underlying point. The heliosphere is not a sphere. It is not a simple shell. Its shape above and below the Sun is physically different from its shape along the ecliptic. Because the solar wind is different over the poles, the interstellar medium presses unevenly from different directions, and the Sun's magnetic field creates asymmetries that change with the solar cycle. The boundary of the Sun's domain, the edge of the region controlled by our star, has three-dimensional structure that is still being mapped. Even the question of where the Sun's influence ends is not a flat question. It depends on which direction you go. What we do know is that directly above the Sun's north pole, if you travel far enough, you leave the heliosphere. You cross into interstellar space, and you enter a region that most people never imagine when they think about the solar system. You enter the ocean between the stars. This ocean is not empty. The interstellar medium is thin, fantastically thin, by earthly standards, but it is not nothing. On average, interstellar space in our neighbourhood contains roughly 1 atom per cubic centimetre. That is a better vacuum than anything ever produced in a laboratory on Earth. But over the vast distances between stars, those sparse atoms add up. They form clouds. They create structure. And the structure directly around the Sun turns out to be surprisingly dramatic. The Sun is currently passing through a small, warm cloud of interstellar gas called the local interstellar cloud. This cloud is roughly 30 light-years across, relatively warm by interstellar standards at about 6,000 degrees, and moving through space at a velocity of roughly 26 kilometers per second relative to the Sun. It is not dense enough to notice from Earth. It does not block starlight or create visible nebulae, but it is there, gently pressing against the heliosphere from the outside, and the Sun is slowly moving through it. Beyond the local interstellar cloud, the picture gets far more interesting. The Sun sits near the center of a vast, low-density cavity in the interstellar medium called the local bubble. This structure, roughly 1,000 light-years across, was carved out of the surrounding gas by a series of supernova explosions over the past 10 to 14 million years. Massive stars in a nearby stellar association lived fast, burned through their fuel, and detonated one after another, their blast waves sweeping up the surrounding interstellar gas and pushing it outward into a dense shell. The interior of this cavity was left nearly evacuated, filled with extremely hot, low-density gas that glows faintly in X-rays. The local bubble is one of the most important and least discussed features of the Sun's neighbourhood, and its shape is directly relevant to the question of what lies above and below the Sun, because the local bubble is not a sphere. Observations from three-dimensional dust mapping, combined with soft X-ray surveys of the sky, reveal that the local bubble is narrower in the galactic plane and wider in the directions above and below it. Its shape has been described as an hourglass or a peanut shell, pinched in the middle where the dense gas of the galactic disk resists the expansion of the cavity, and flaring outward in the directions perpendicular to the disk, where less resistance allowed the bubble to expand more freely. Some recent studies go further, suggesting the local bubble may not be closed at all in the vertical directions. It may be open-ended above and below the galactic plane, forming what astronomers call a chimney, a tube of hot, low-density gas venting from the galactic disk up into the galactic halo. Think about what this means. The Sun sits inside a cavity that is elongated vertically, stretched above and below the galactic plane. If you travel directly above the Sun in galactic terms, heading toward the North Galactic Pole, you may be traveling along the long axis of the local bubble, through the direction where the cavity extends farthest. You would be moving through some of the emptiest, least dense space in the Sun's entire neighbourhood, a corridor blown open by ancient supernovae that funnels hot gas upward out of the galactic disk. This is hidden vertical structure. It exists directly above and below the Sun, but no flat diagram of the solar system ever mentions it. The local bubble is not part of the solar system. It is an interstellar feature, a cavity between the stars. But the Sun lives inside it right now, and its shape defines the three-dimensional environment that surrounds our star on scales of hundreds of light years. Above and below the Sun, in the galactic sense, the local bubble opens outward like a funnel, connecting the Sun's neighbourhood to the vastly larger space above and below the Milky Way's disk. The Sun has not always lived inside this cavity. Before arriving here, it travelled through denser regions of the interstellar medium, where the gas pressing against the heliosphere was thicker and the boundary of the Sun's domain was compressed closer in. Inside the local bubble, with so little surrounding gas to resist the outward push of the solar wind, the heliosphere may be slightly larger than it would be in a denser environment. The Sun is essentially floating in a cleared room, its protective bubble stretching a little farther into the emptiness than it otherwise could. The Sun's environment changes as it moves through the galaxy, and its current residence inside this ancient supernova remnant is temporary on cosmic timescales. But the local bubble did more than just empty out the Sun's neighbourhood. It built the neighbourhood we see today. In 2022, a team led by astronomer Catherine Zucker published a landmark study that mapped the three-dimensional positions of nearby molecular clouds, the dense clumps of gas and dust where new stars are born. They found something remarkable. Virtually every major star-forming region within about 650 light-years of the Sun sits on the surface of the local bubble's expanding shell. Taurus, Perseus, Ophiuchus, the clouds in Scorpius Centaurus, all of them are arranged on the skin of the bubble like cities built along a coastline. The implication is stunning. The same supernova explosions that carved the local bubble also triggered the formation of the very stars and nebulae that fill our sky today. As those explosions drove material outward, they piled it into dense sheets and filaments at the expanding rim. That concentrated gas became gravitationally unstable and began collapsing into new stars. The star-forming regions around us are not randomly scattered. They are the debris rim of an ancient series of explosions, organized on the surface of a cavity that the explosions themselves created. The Sun played no role in this. It was not here when the supernovae went off 14 million years ago. It drifted into the local bubble later, carried by its orbit around the galactic center. The Sun is a visitor inside a structure built by dead stars, and that structure has a three-dimensional shape that matters enormously for our question, because the bubble's shell, the ring of star-forming clouds, is not confined to the galactic plane. It extends above and below it. This connects to another feature of the Sun's neighbourhood that astronomers puzzled over for more than a century. The Gould Belt is a ring of young, bright stars surrounding the Sun, tilted about 18 degrees to the galactic plane. Discovered in the 1800s, the The Gould Belt was long considered a distinct structure, a mysterious band of recent star formation encircling the Sun at a jaunty angle to the Milky Way's disk. Its origin was unclear. Why would young stars form in a ring tilted to the galactic plane? What organized them? The three-dimensional dust maps that revealed the local bubble's shape may have answered this question. The Gould Belt appears to correspond closely to the expanding shell of the local bubble. The ring of young stars is not a separate structure at all. It is the surface of the bubble, the compressed rim where star formation was triggered, seen from inside. Its tilt relative to the galactic plane reflects the fact that the local bubble itself is tilted, its expansion asymmetric, its shape influenced by the uneven distribution of gas in the interstellar medium that the supernova blast waves encountered. This means the tilted ring of bright young stars surrounding the Sun, a feature visible to the naked eye as the brightest stars in Scorpius, Orion, and other nearby constellations, is actually the inner wall of a three-dimensional cavity. It is structure above and below the galactic plane, organized by explosions, shaped by the vertical density gradient of the galaxy's disk, and visible from Earth only because we happen to be sitting inside it. The Sun's neighborhood is not a random scattering of stars. It is the interior of a sculpted cavity with walls that extend above and below, a three-dimensional architecture carved by violence and maintained by the thinness of the surrounding gas. But there is another structure above and below the Sun that most people forget entirely, even though it technically belongs to the solar system itself: the Oort Cloud. Everyone knows about the Kuiper Belt, the ring of icy bodies beyond Neptune where Pluto lives. The Kuiper Belt gets mentioned in every documentary and every textbook diagram. But the Kuiper Belt is flat. It hugs the ecliptic, extending only modestly above and below the orbital plane. It is part of the disk, part of the flat picture, part of the two-dimensional story that diagrams love to tell. The Oort Cloud is different. It is believed to be a vast, roughly spherical shell of icy objects surrounding the solar system at distances ranging from roughly 2,000 to as far as 100,000 astronomical units from the Sun. At those distances, the Sun's gravity is barely strong enough to hold objects in orbit. The outermost Oort Cloud objects are so weakly bound that a passing star's gravity can nudge them inward, sending them falling toward the inner solar system as long-period comets. The critical point is the shape. The Oort Cloud is not flat. It does not hug the ecliptic. It extends equally in all directions, above, below, and to every side. If you travel directly above the Sun, perpendicular to the ecliptic, you do not escape the solar system's material as quickly as the flat diagrams suggest. You pass through the Kuiper Belt's thin disk almost immediately, yes. But then you enter the Oort Cloud, a shell of trillions of frozen bodies that extends above the Sun for an estimated 1 to 2 light-years in every direction. The Oort Cloud has never been directly observed. No telescope has imaged an Oort Cloud object in its distant orbit. Its existence is inferred from the orbits of long-period comets that arrive from every direction, not just from the ecliptic, with orbital periods of thousands or millions of years. These comets must come from a vast spherical reservoir, because their orbital inclinations are random. They have no preference for the ecliptic plane. They fall inward from above, below, and every angle in between. But why is the Oort Cloud spherical in the first place? This is a question most people never think to ask, and the answer reveals something deep about how the solar system's three-dimensional structure was built. The objects in the Oort Cloud did not form there. They formed much closer to the Sun, in the same flat disk of gas and dust that produced the planets. Early in the solar system's history, the region around the giant planets was crowded with billions of small icy bodies, leftover building material that never coalesced into a planet. These objects orbited in the ecliptic plane, just like everything else. They were flat. They were part of the disk. Then the giant planets scattered them. Jupiter, Saturn, Uranus, and Neptune are so massive that any small body passing close to them receives a powerful gravitational kick. Some of these kicks sent icy bodies plunging inward toward the Sun. Others flung them outward, far from the ecliptic, into elongated orbits that carried them thousands or tens of thousands of astronomical units from the Sun. These scattered orbits were no longer confined to the ecliptic. The gravitational kicks came from random directions during close encounters, and the resulting orbits tilted to every possible inclination. The flat disk of icy material was being launched into three-dimensional space, but scattering alone would produce a puffy cloud, not a perfectly spherical one. The final ingredient is the galactic tide. At distances of tens of thousands of astronomical units from the Sun, the gravitational pull of the Milky Way itself becomes significant compared to the Sun's weakened gravity. The galaxy's tidal forces, the differential gravitational pull from the disk of the Milky Way, slowly torque the orbits of Oort Cloud objects over millions of years. These torques randomize the orbital inclinations even further, erasing any remaining memory of the original ecliptic plane. Passing stars add to this process, nudging orbits into new orientations each time a neighboring star drifts within a light year or two of the Sun. The result is a spherical shell, the flat disk's own material redistributed into three dimensions by gravity. The Oort Cloud is the solar system's memory of a violent youth, billions of icy bodies that started in the ecliptic plane and were flung above and below it by planetary encounters and galactic forces over billions of years. Its spherical shape is proof that the solar system's three-dimensional structure is not a quirk or an afterthought. It is a consequence of the fundamental physics that governs how small bodies interact with massive planets and with the galaxy itself. This means that directly above the Sun, in the ecliptic frame, the solar system does not end at the edge of the Kuiper belt. It continues outward for the vast distance we described earlier, wrapped in a spherical shell of frozen material that most diagrams never show. The Oort Cloud is the solar system's hidden vertical dimension, the part of our star's gravitational territory that extends equally above and below, quietly contradicting the flat picture at the largest local scales. This means that even in the solar system's own terms, the space above and below the Sun is not truly empty. The disk of planets and asteroids is flat, yes, but surrounding that flat disk is an enormous spherical haze of frozen material that no flat diagram ever shows. The Oort Cloud is the solar system's third dimension, the part of our star's gravitational domain that extends equally above and below, contradicting the flat picture at the largest scales. If the Oort Cloud extends 1 to 2 light-years above and below the Sun, it reaches a significant fraction of the distance to the nearest star. The outer Oort Cloud may extend nearly halfway to Proxima Centauri, the closest star to the Sun whose distance we already know. In fact, neighbouring stars probably have their own Oort Clouds, and in the tightest stellar neighbourhoods those clouds may nearly overlap. The boundaries between one star's gravitational territory and another's are not clean lines drawn on a map. They are fuzzy, overlapping shells of icy debris, extending in all three dimensions, including the ones that every flat diagram deletes. Now, consider the stellar neighbourhood itself. The nearest stars to the Sun are not arranged in a plane. They are scattered in three dimensions, distributed above, below, and to all sides of the ecliptic. Proxima Centauri sits below the ecliptic plane. Barnard's star sits above it. Sirius also sits well below it, but in an entirely different direction. The stars within 10 light-years of the Sun form a small three-dimensional cloud with no preferred orientation, no alignment with the ecliptic, no respect for the flat diagram's implied flaw. If you could build a three-dimensional model of the Sun's neighbourhood, with the Sun at the centre and nearby stars represented as tiny lights scattered around it, the model would look nothing like the flat diagram. Stars would float above and below. Some would sit at steep angles to the ecliptic. The model would be fully three-dimensional, a cloud of points in space, and the ecliptic would be just one thin plane slicing through that cloud, relevant only to the Sun's own planetary family and meaningless to every other star in the neighbourhood. This is the reality that the flat picture erases. The solar system's immediate environment is three-dimensional in every sense. The heliosphere is shaped differently above the poles than along the equator. The interstellar medium has real structure. The local interstellar cloud, the local bubble, the chimney opening above and below the galactic disk. The Oort Cloud wraps around the Sun in a sphere, not a disk. The nearby stars float in a three-dimensional volume, unaligned with the ecliptic. Every one of these features has vertical extent. Every one occupies the space above and below the Sun, and every one is invisible in the flat diagrams that shape how most people picture their cosmic neighbourhood. But all of this, the heliosphere, the Oort Cloud, the local bubble, the nearby stars, is still a tiny neighborhood. The Sun belongs to a galaxy, and the galaxy has its own plane, its own vertical structure, and its own version of above and below. We already established that the ecliptic is tilted 60 degrees from the galactic plane. That means when we switch reference frames and start asking what lies above and below the Sun in galactic terms, we are looking in a dramatically different direction. And in that direction, the structures are not small, they are not local, they are not subtle. Directly above the Sun in galactic terms, looking perpendicular to the disk of the Milky Way toward the North Galactic Pole in Coma Berenices, the universe opens into structures spanning tens of thousands of light years. The galactic halo, globular clusters older than the Earth, satellite galaxies being torn apart by tidal forces, enormous bubbles of high-energy particles driven by eruptions from the galactic center. And beneath it all, a dark matter envelope extending hundreds of thousands of light years in every direction, invisible and massive, scaffolding the entire galaxy. The solar system's local three-dimensional structure was hidden by the flat diagram. The galaxy's vertical structure is hidden by something even more powerful: our inability to see past the blinding clutter of the galactic disk itself. But the structures are there. They are confirmed. And they begin directly above and below where we sit right now, waiting to be explored. Everything we have explored so far, the heliosphere, the solar wind streaming over the Sun's poles, the Oort Cloud wrapping the solar system in a spherical shell, the local bubble with its chimney opening above and below the galactic disk, all of it is local, cosmically local. The heliosphere is a speck. The local bubble is a small cavity in one arm of one galaxy. Even the nearest stars are our immediate neighbours, separated from the Sun by distances that the Milky Way would barely notice. We have been standing in the front yard and describing the garden fence. Now it is time to step back and look at the entire city. The Milky Way is a barred spiral galaxy, roughly 100,000 light-years across and about 1,000 light-years thick in the disk. It contains approximately 400 billion stars arranged in spiral arms that wind outward from a central bar of densely packed stars. The Sun sits within one of these arms, called the Orion Arm, at a distance of roughly 26,000 light-years from the galactic center. From above, if you could somehow look down on the galaxy like a map, the Sun would be an utterly unremarkable point about halfway between the center and the visible edge, lost among billions of similar stars. But we cannot look down on the galaxy. We are inside it. And this is where the question of above and below becomes genuinely disorienting, because the galaxy has its own plane, its own equator, its own poles, and they have almost nothing to do with the solar system's ecliptic. We touched on this earlier. The ecliptic, the solar system's orbital plane, is tilted approximately 60 degrees to the galactic plane. Now, it is time to feel what that tilt actually means in three-dimensional space. The galactic plane is defined by the disk of the Milky Way, the flat structure where most of the galaxy's stars, gas, and dust are concentrated. Perpendicular to this plane, straight up from the disk, is the direction called the North Galactic Pole. The International Astronomical Union defined the position of the North Galactic Pole in 1958. It points toward the constellation Coma Berenices, near the bright star Arcturus. The South Galactic Pole points in the opposite direction, toward the constellation Sculptor, deep in the southern sky. These galactic poles define above and below for the galaxy, and they point in completely different directions from the ecliptic poles. The North Ecliptic Pole, as we discussed, points toward Draco. The North Galactic Pole points toward Coma Berenices. These two directions are separated by about 60 degrees on the sky. If you stood on the Sun and pointed one arm toward ecliptic north and the other toward galactic north, your arms would be spread wide apart, forming an angle that looks nearly like a right angle. The two versions of up are dramatically different. This is not an abstraction. It has physical consequences. When you look toward the North Ecliptic Pole, you are looking through the galactic disk at a steep diagonal. Stars, gas, and dust from the Milky Way's disk are scattered across your line of sight. But when you look toward the North Galactic Pole, you are looking straight out of the disk, perpendicular to it, through the thinnest possible cross-section of the galaxy. The disk clears out quickly in that direction, Within a few hundred light years, you have passed through most of the galaxy's thin disk of young stars and gas. Within a few thousand, you have left even the older thick disk behind, and then you are looking into the galactic halo, a vast, sparse, roughly spherical volume of space that extends above and below the disk for tens of thousands of light years. The galactic poles are the cleanest windows out of the Milky Way. They are the directions where the galaxy's own clutter gets out of the way most quickly, allowing astronomers to see deep into intergalactic space. This is not a coincidence. It is geometry. The disk is thin. Looking perpendicular to it means looking through the least amount of material. Some of the most important deep observations in the history of astronomy, including the Hubble Deep Fields, were deliberately aimed near the galactic poles to minimize interference from the Milky Way's own stars and dust. But before we look into deep space, we need to understand the vertical structure of the galaxy itself. Because directly above and below the Sun in galactic terms, real, confirmed physical structures exist that almost no one outside astronomy ever thinks to picture. Start with the Sun's exact position. The Sun does not sit precisely in the galactic midplane. It is offset slightly to the north, currently located approximately 20 parsecs, or roughly 65 light-years, above the galactic equator. This is a tiny offset compared to the galaxy's overall thickness, but it is real and measurable. Multiple independent studies using stellar parallaxes, star counts, and even gamma-ray observations have confirmed this displacement. The Sun is slightly above the galactic plane right now, leaning toward galactic north, and the Sun does not stay put. As it orbits the galactic center, it simultaneously oscillates up and down through the galactic disk, bobbing above and below the midplane in a slow vertical cycle. The gravitational pull of the mass concentrated in the disk acts like a restoring force. When the Sun drifts above the plane, the gravity of the disk pulls it back down. It crosses through the midplane, overshoots below, gets pulled back up, crosses through again, overshoots above, and repeats. The full cycle takes roughly 60 to 70 million years, and the Sun reaches a maximum height of approximately 250 light-years above or below the midplane at the peak of each oscillation. The Sun crossed through the midplane a few million years ago, and what has happened since then deserves a closer look. This oscillation is not just a curiosity. Some researchers have proposed that the Sun's passage through the galactic midplane, where the density of gas and dust is highest, might correlate with periods of increased comet impacts on Earth, because the denser environment could gravitationally disturb Oort Cloud objects and send them falling inward. The hypothesis remains unconfirmed and debated, but the oscillation itself is well established. The Sun moves vertically through the galaxy on a cycle that is shorter than a single galactic orbit, like a horse on a carousel rising and falling as it circles. The mechanism behind this oscillation is elegant in its simplicity. The galactic disk concentrates most of its mass in a thin layer near the midplane. When the Sun is exactly in the midplane, the gravitational pull from the disk is symmetric, equal amounts of mass above and below, and there is no net vertical force. But the moment the Sun drifts slightly above the midplane, there is more mass below it than above it. The excess mass pulls it downward, back toward the plane. The Sun accelerates downward, crosses the midplane, and overshoots to the south side. Now there is more mass above it than below, and gravity pulls it back up. The cycle repeats, endlessly, the mass of the galactic disk acting as a restoring force, exactly the way a spring pulls a weight back to its resting position. At the peak of each swing, the Sun reaches the maximum height noted earlier, roughly the distance a beam of light would cross in 2.5 centuries. Right now, the Sun is steadily heading northward from the position we just described. Still in the early upward phase of its current swing through the disk, it will continue rising for approximately another 15 million years before reaching its maximum height, slowing, stopping, and then falling back toward and through the galactic plane. The period of the oscillation, roughly 60 to 70 million years for a full cycle, is determined by the density of matter in the galactic disk near the Sun's location. A denser disk produces a stronger restoring force in a shorter period, the same way a stiffer spring oscillates faster. Measuring the oscillation period therefore gives astronomers an independent way to estimate the local mass density of the galaxy, including contributions from dark matter in the disk that cannot be seen directly. The observed period is consistent with a local mass density of about 0.15 solar masses per cubic parsec, a value that includes stars, gas, dust, and a modest contribution from dark matter within the disk. The speculative connection between this oscillation and events on Earth has attracted attention for decades, though it remains unconfirmed. In 1984, researchers proposed that the Sun's passage through the galactic midplane might correlate with periods of increased comet bombardment on Earth. The idea is that the denser environment near the midplane, where molecular clouds and other massive objects are more common, could gravitationally perturb Oort Cloud objects, sending some of them tumbling inward on collision courses with the inner planets. The roughly 30 to 35 million year interval between midplane crossings has been compared to a claimed periodicity in mass extinction events in the fossil record, but both the extinction periodicity and the proposed causal mechanism remain subjects of active debate. The correlation is suggestive but not established. What is established, firmly, is that the Sun does not travel through the galaxy on a flat path. It rises and falls rhythmically through the disk of the Milky Way, and its vertical position at any given moment determines what kind of galactic environment it is passing through. Now look upward in the galactic frame. You are the Sun, sitting 65 light-years above the midplane, and you look straight toward the North Galactic Pole. What do you see? First, you pass through the remainder of the thin disk. The thin disk is the youngest, most active layer of the Milky Way, containing most of the galaxy's gas, dust, star-forming regions, and young stars. It has a scale height of roughly 300 to 400 light-years, meaning most of its material is concentrated within that distance above and below the midplane. Since the Sun is only 65 light-years above the midplane, you still have a couple hundred light-years of thin disk above you before you emerge from it. As you rise above the thin disk, you enter the thick disk. This is an older, puffier population of stars that extends roughly 3,000 to 6,000 light-years above and below the midplane. Thick disk stars are generally older than thin disk stars, with lower metallicity, meaning they contain fewer heavy elements. They orbit the galactic center on paths that are slightly more inclined and eccentric than thin disk orbits, which is why they spread out to greater heights. The thick disk is not a sharp boundary. It blends gradually into the thin disk below and the halo above, but it represents a distinct population of stars with its own chemical and kinematic signature. Keep climbing. Beyond the thick disk, you enter the galactic halo. This is a vast, roughly spherical volume of space that surrounds the entire disk of the Milky Way. The halo extends at least 50,000 light-years above and below the galactic plane, and in terms of dark matter, it reaches much farther. The stellar halo, the part containing visible stars, is sparse. Only about 1% of the galaxy's total stellar mass resides in the halo, but what it lacks in density, it makes up for in age. And in the stories it tells about the galaxy's history, the halo contains roughly 150 known globular clusters. These are dense, ancient spheres of stars, each containing hundreds of thousands to millions of stars packed into a volume only a few dozen light-years across. Globular clusters are among the oldest objects in the galaxy. Many formed over 12 billion years ago, when the Milky Way was still assembling itself from smaller protogalactic fragments. They orbit high above and below the disk, some reaching distances of tens of thousands of light-years from the galactic plane. The cluster, known as Messier 13, one of the most famous globular clusters visible from the northern hemisphere, orbits through the halo at a distance of roughly 22,000 light-years from the Sun. These clusters are directly above and below the Sun in galactic terms. They are part of the vertical structure of the Milky Way, objects that exist in the directions the flat diagram never shows. When you look straight up from the galactic disk, you are looking into a sparse swarm of ancient star clusters orbiting the galaxy in 3 dimensions, tracing paths that carry them high above the disk, and then plunging them back through it. The halo also contains individual old stars, many of them RR Lyrae variable stars and metal-poor subdwarfs. These halo-field stars are scattered thinly through the volume above and below the disk. They move on highly eccentric, highly inclined orbits, passing through the disk and then arcing far above or below it. Some are remnants of smaller galaxies that the Milky Way devoured billions of years ago, Their chemical compositions carry the signatures of their birthplaces, foreign galaxies that no longer exist as independent systems. These stars are ghosts of galactic cannibalism, drifting above and below the disk as evidence of ancient collisions. But globular clusters and old stars are only part of the story. Directly above and below the galactic center, towering over the disk of the Milky Way, are structures that were discovered only in the last 15 years. Structures so enormous they dwarf anything in the Sun's local neighborhood. In 2010, scientists using data from the Fermi Gamma Ray Space Telescope announced the discovery of two enormous lobes of high-energy emission extending above and below the galactic center. These structures, now called the Fermi bubbles, reach approximately 25,000 light-years above the galactic plane and 25,000 light-years below it. Together they span roughly 50,000 light-years from top to bottom, half the diameter of the entire galactic disk. They are roughly circular when viewed from the side, symmetric about the galactic center, and filled with relativistic charged particles emitting gamma rays with energies in the billions of electron volts. Then in 2020, the eRosita X-ray telescope, aboard the Spectrum X Gamma Space Observatory, revealed something even larger. The eRosita bubbles extend approximately 80 degrees above and below the galactic plane, reaching even farther than the Fermi bubbles. These structures are visible in soft X-rays, glowing with the thermal emission of superheated gas at temperatures of millions of degrees. The eRosita bubbles appear to encase the Fermi bubbles, forming an even larger hourglass of hot gas driven outward from the galactic center. The leading explanation for both sets of bubbles is an enormous energy outburst from Sagittarius I star, the supermassive black hole at the center of the Milky Way. This black hole, with a mass of roughly 4 million times the mass of our Sun, is currently quiet. But a few million years ago, it may have undergone a period of intense activity, consuming large amounts of material and releasing colossal jets of energy perpendicular to the galactic disk. Those jets inflated the Fermi bubbles with cosmic ray particles and drove a shockwave outward through the surrounding gas, creating the eRosita bubbles in the process. The discovery of the Fermi bubbles is one of the most remarkable detective stories in modern astrophysics. The bubbles were not found by pointing a telescope at a specific target. They were found by subtraction. The Fermi Gamma Ray Space Telescope surveys the entire sky continuously, mapping every source of high-energy gamma ray emission. When scientists built a model of all known gamma-ray sources, the diffuse glow of the Milky Way's disk, individual pulsars, distant blazars, supernova remnants, and subtracted that model from the actual data, they expected to see noise, random fluctuations. Instead, they found two enormous symmetric lobes of gamma-ray emission rising above and below the galactic center like a pair of lungs. The signal had been hiding in plain sight, buried beneath the clutter of other sources, waiting for someone to peel away the layers and see what remained. The physical difference between the Fermi bubbles and the eRosita bubbles is important and often confused. The Fermi bubbles are filled with relativistic particles, protons and electrons accelerated to nearly the speed of light. These particles produce gamma-ray emission as they interact with ambient light and gas, either through inverse Compton scattering, where fast electrons boost low-energy photons to gamma-ray energies, or through collisions between relativistic protons and ordinary gas that produce particles called pions, which then decay into gamma rays. The exact mechanism is still debated, but the key point is that the Fermi bubbles represent a population of extraordinarily energetic particles confined within sharp boundaries high above and below the galactic plane. The eRosita bubbles are different. They are filled primarily with hot thermal gas, plasma heated to temperatures of several million degrees that emits soft X-rays. This gas is not moving at relativistic speeds. It is simply extremely hot, heated by the same energetic event that created the Fermi bubbles. The leading explanation is that the jets or outflows from Sagittarius A star inflated the Fermi bubbles with cosmic rays, and those cosmic rays drove a shock wave outward through the surrounding galactic gas, compressing and heating it to create the larger eRosita bubbles. The Fermi bubbles sit inside the eRosita bubbles, like a kernel inside a shell, each one a different physical signature of the same ancient eruption. The competing hypotheses about what caused the eruption add another layer. One school of thought argues the bubbles were produced by jets from Sagittarius A star during a period of active accretion a few million years ago, when the black hole was consuming large quantities of gas and releasing enormous energy in tightly focused beams perpendicular to the galactic disk. Another school proposes that a burst of intense star formation near the galactic center produced enough supernovae and stellar winds to drive the outflow without any help from the black hole. Both scenarios can reproduce the general size and shape of the bubbles in computer simulations. Distinguishing between them requires precise measurements of the bubble's chemical composition, magnetic field structure, and energy content, measurements that current and upcoming X-ray observatories are working to provide. What matters for our story is simpler. Directly above and below the galactic center, extending 25,000 light-years in each direction, confirmed structures of extreme energy exist. They are not hypothetical. They have been mapped. They have sharp edges. They contain more energy than millions of supernova explosions. And they occupy the directions that the flat diagram of the Milky Way never shows. The vertical directions, the ones that point straight out of the disk into the space above and below. These structures are directly above and below the galactic center. The Sun is offset from the center by 26,000 light-years, so the bubbles are not directly overhead from our vantage point, but they extend so far above and below the disk that parts of them reach into the sky above and below the Sun's position as well. They are part of the vertical architecture of the galaxy, enormous features that exist in the directions perpendicular to the disk, real confirmed structures detected by space telescopes, and completely absent from every flat diagram of the Milky Way you have ever seen. Keep going. Beyond the stellar halo, beyond the bubbles, even beyond the farthest globular clusters, the Milky Way has more structure above and below. Satellite galaxies, the Milky Way is orbited by dozens of smaller galaxies, gravitationally bound companions that trace paths through the halo at various distances and inclinations. The Large Magellanic Cloud, visible to the naked eye from the southern hemisphere, orbits at a distance of roughly 160,000 light-years. The Small Magellanic Cloud sits nearby at about 200,000 light-years. These are substantial galaxies in their own right, containing billions of stars. Then, there are the dwarf galaxies. The Sagittarius Dwarf Elliptical Galaxy, which we will return to shortly, is being slowly devoured by our galaxy, its stars unravelling into long tails that wrap around the Milky Way. The Ursa Minor Dwarf, the Draco Dwarf, the Carina Dwarf, the Sextans Dwarf, and many others orbit through the halo at various heights above and below the galactic plane. In recent years, surveys using the Gaia spacecraft and large ground-based telescopes have discovered dozens of ultra-faint dwarf galaxies, tiny systems containing only a few thousand stars each, orbiting at enormous distances from the galactic center. Some of these satellite galaxies orbit at heights far above the galactic disk. They exist in the vertical space above and below the Sun in galactic terms. They are part of the three-dimensional structure of the Milky Way system, real galaxies occupying the directions that the flat picture ignores, and many of them are doomed. The Milky Way is gradually devouring its satellites, stripping their stars through tidal forces and absorbing them into the halo. The streams of stars left behind by these disrupted galaxies crisscross the halo in every direction, including straight above and below the disk, creating an intricate web of stellar debris that records billions of years of galactic cannibalism. The Sagittarius stream deserves particular attention because it is the most vivid example of three-dimensional structure above and below the galactic disk. The Sagittarius Dwarf Elliptical Galaxy, a small galaxy roughly 10,000 light-years in diameter, is currently being torn apart by the Milky Way's tidal forces. It sits on the far side of the galactic center from us, partially hidden behind the dense star fields of the disk. As it orbits, the Milky Way's gravity stretches it like taffy, pulling stars from its leading and trailing edges into two long tidal tails that wrap around the entire galaxy. These tails, collectively called the Sagittarius stream, have been mapped using surveys of stellar positions and velocities. The stream does not stay in the galactic plane. It arcs far above and below the disk, reaching heights of 50,000 to 70,000 light-years above the midplane at its most distant points. If you could see the stream with your naked eye, it would stretch across the entire sky, a great circle of stars threading over and under the galaxy like thread wound loosely around a ball. The stream contains roughly 100 million stars, all of them former citizens of the Sagittarius dwarf that were stripped away over the past 2 to 3 billion years of orbital decay. Some of these stars are now directly above the Sun in galactic terms, drifting through the halo at enormous heights, following orbital paths that will carry them around the galaxy for billions of years before they are fully absorbed into the Milky Way's general population. The Sagittarius stream is not unique. Other streams crisscross the halo, remnants of other devoured galaxies, some so ancient that the parent galaxy has been completely dissolved and only the stream remains as a fossil. The halo above and below the Sun is not an empty void populated by a few scattered old stars. It is a graveyard and a crime scene, threaded with the remains of galaxies that wandered too close to the Milky Way and paid the price. Each stream is a line of evidence, a record of a collision written in the positions and velocities of millions of stars orbiting high above and below the disk. And beneath all of this visible structure lies the dark matter halo. The Milky Way's dark matter halo is a massive, roughly spherical envelope of invisible matter that extends far beyond everything we can see. Its exact extent is debated, but conservative estimates place its radius at roughly 650,000 light-years, with some models suggesting it may reach 1 million light-years or more. This halo contains roughly 10 times the mass of all the visible stars, gas and dust in the galaxy combined. It is the gravitational scaffolding that holds everything together, the reason the galaxy's rotation curve stays flat at large distances, the reason satellite galaxies remain in orbit rather than drifting away. Directly above and below the Sun in galactic terms, this dark matter halo extends for hundreds of thousands of light-years. It is invisible, it emits no light, absorbs no light, and interacts with ordinary matter only through gravity. Dark matter particles, whatever they are, stream through the Sun, through the Earth, through your body at this very moment, trillions of them every second, passing through ordinary matter like ghosts because they interact so weakly that they might as well not be there at all, and yet their collective gravity dominates the mass budget of the galaxy, shaping its structure on the largest scales. If you could somehow see dark matter, the Milky Way would look completely different from any image you have ever seen. The thin, bright disk of stars would be a tiny feature embedded at the center of an enormous, dim, spherical cloud of dark matter extending in every direction, above, below, and to all sides, for hundreds of thousands of light-years. The bright galaxy we photograph and admire is a thin, luminous core inside a vastly larger, invisible structure. The true galaxy is mostly dark, mostly spherical, and mostly vertical. The disk is a detail, the halo is the main event. This is what lies above and below the Sun in galactic terms, not empty space. Not a vague continuation of more of the same, a specific, layered, structured architecture of increasing scale and decreasing visibility. The thin disk, the thick disk, the stellar halo with its ancient globular clusters and streams of cannibalized galaxies, the Fermi and Rosetta bubbles towering over the galactic center, satellite galaxies orbiting through the halo at distances of hundreds of thousands of light-years, and surrounding everything, an invisible dark matter envelope that extends farther than any visible structure and contains more mass than everything you can see combined. The flat diagram showed you a disk, a thin, clean, two-dimensional plane of stars and planets. What it did not show you is that this disk is embedded in a three-dimensional structure that extends just as far above and below as it does from side to side. The galaxy is not a disk, it is a disk inside a sphere. And the sphere, the part that includes the halo, the satellites, and the dark matter, is the larger component by far. Every direction from the Sun leads somewhere, but the directions above and below, the ones the flat diagram erased, lead into the deepest and most massive structures of the galaxy. They lead through layers of increasingly ancient material, from the young stars of the thin disk to the primordial globular clusters of the halo. They lead past the scars of galactic violence, the bubbles blown by the central black hole, the streams left by devoured galaxies, and they lead into the dark matter halo, the invisible foundation that holds it all together. If you could point a powerful telescope straight toward the North Galactic Pole in Coma Berenices and take a long exposure, what would you see? First, a scattering of foreground stars, relatively bright, relatively nearby, members of the Milky Way's thin disk and halo that happen to lie along that line of sight. But compared to any direction along the galactic plane, these foreground stars are sparse. The disk thins rapidly as you look perpendicular to it. Within a degree or two of the pole, the Milky Way's own stars become an afterthought. Behind them, the frame fills with galaxies, thousands of them, tens of thousands in a deep enough exposure. Spirals, ellipticals, irregulars, galaxy clusters glowing with the combined light of hundreds of member galaxies. The North Galactic Pole direction is one of the richest fields for extragalactic astronomy, precisely because the Milky Way steps aside. The Coma cluster, one of the nearest rich galaxy clusters, lies in this general direction, roughly 320 million light-years away, containing over 1,000 large galaxies and countless dwarfs bound together by gravity and embedded in superheated gas visible in X-rays. The South Galactic Pole, in the constellation Sculptor, offers a similar window. Sculptor is known among astronomers for its clean, uncluttered view into deep space. The Sculptor dwarf galaxy, a satellite of the Milky Way, sits in this direction, as do numerous background galaxy groups visible through the sparse foreground. These galactic pole directions are where the vertical dimension of the universe reveals itself most directly. Looking along the disk, you see the Milky Way's own structure, rich, detailed, but obscuring. Looking perpendicular to the disk, you see past the galaxy, through it, into the depths of cosmic space. The view above and below is the clear view. It is the direction where the universe opens up, and the Sun's membership in a much larger architecture becomes undeniable. But even the dark matter halo is not the end. The Milky Way does not float alone in empty space. It belongs to a group, and that group belongs to a supercluster, and that supercluster is threaded into the cosmic web that spans the observable universe. Above and below the Sun, at the very largest scales, the galaxy's own orientation becomes just one more local quirk, and the structures that appear overhead belong not to the Milky Way but to the architecture of the cosmos itself. We have travelled directly above the Sun in two different reference frames. In the ecliptic frame, we rose perpendicular to the solar system's orbital plane and found barren interplanetary space within a few astronomical units, the thin disk of planets falling away almost immediately. In the galactic frame, we rose perpendicular to the Milky Way's disk and passed through layers of increasing age and decreasing density. The thin disk, the thick disk, the stellar halo with its ancient globular clusters, the Fermi and Erosita bubbles, satellite galaxies, and the invisible dark matter envelope extending hundreds of thousands of light-years in every direction. But neither frame is the final one. The Milky Way itself is not the largest structure the Sun belongs to, and when you keep travelling upward, past the dark matter halo, past the outermost satellite galaxies, past the last gravitational whisper of our galaxy, you do not enter featureless void. You enter the architecture of the cosmos, and the directions above and below the galactic plane turn out to be among the most revealing windows we have for seeing it. Here is why. The galactic disk is full of obstructions. Stars, gas clouds, and interstellar dust crowd the plane of the Milky Way, absorbing and scattering light from distant objects. If you try to look outward along the galactic plane, your view is blocked within a few thousand light-years in most directions. The galactic center itself is invisible in optical light, hidden behind thick curtains of dust. Entire regions of the sky along the Milky Way's band are called the zone of avoidance by astronomers, because so few distant galaxies can be seen through the clutter. But look perpendicular to the disk, toward the galactic poles, and the obstruction drops dramatically. Within a few hundred light-years above or below the midplane, you have passed through most of the galaxy's dust. The sky clears, the view opens, and suddenly you can see not just out of the Milky Way, but deep into the universe beyond. This is not just a theoretical observation. It has shaped the history of astronomy in practical ways. When the Hubble Space Telescope team chose the location for the Hubble Deep Field, one of the most important astronomical images ever taken, They deliberately selected a patch of sky at high galactic latitude, away from the disk, where the Milky Way's own stars would not fill the frame with foreground clutter. The result was an image containing thousands of distant galaxies in a patch of sky smaller than a grain of sand held at arm's length. Those galaxies were visible precisely because the observers looked above the galactic plane, through the thin direction where the Milky Way gets out of its own way. The galactic poles are keyholes. They are the directions where the galaxy's own structure thins to almost nothing, and the depths of the universe become accessible. Directly above and below the Sun in galactic terms, the cosmos is most transparent, and what lies beyond that transparency is the full three-dimensional web of the universe. The Sun belongs to the Milky Way. The Milky Way belongs to the local group, a collection of over 80 galaxies bound together by gravity within a volume roughly 10 million light-years across. The local group is dominated by two large spiral galaxies, the Milky Way and Andromeda, with the smaller Triangulum galaxy as a distant third. The remaining members are dwarf galaxies, scattered in 3 dimensions throughout the group's volume. The local group has no preferred alignment with the Milky Way's disk. Its member galaxies are distributed above, below, and to all sides of the galactic plane. Andromeda sits roughly in the galactic plane as seen from our position, but many dwarf galaxies orbit at high galactic latitudes, visible only when you look above or below the disk. The three-dimensional structure of the local group extends fully into the directions that the flat diagram erases. Zoom out further. The local group itself is falling toward a much larger concentration of mass. It belongs to the Lernia supercluster, a vast gravitational basin roughly 500 million light-years across, containing over 100,000 galaxies. Lernia was identified in 2014 by mapping the peculiar velocities of thousands of galaxies, tracing the gravitational flows that pull everything in our cosmic neighborhood toward a common center of attraction. The Milky Way, the local group, and thousands of other galaxy groups are all streaming together within this enormous structure, drawn by gravitational currents that override cosmic expansion on these scales. Lernia has no alignment with the Milky Way's disk. Its structures, filaments, and walls of galaxies separated by vast voids extend in every direction, including straight above and below the galactic plane. When you look toward the North Galactic Pole in Coma Berenices, you are looking out through the galactic keyhole into the Lernia supercluster and the cosmic web beyond. Galaxy clusters, filaments, and voids fill that direction, stretching to the limits of observation. And this is where the question of above and below transforms into something the flat diagram could never have anticipated. The cosmic web, the largest scale organization of matter in the universe, consists of dense filaments of galaxies, connected at nodes where galaxy clusters form, separated by enormous voids that contain almost nothing. This web has no preferred plane. It extends in all 3 dimensions without any alignment to the Milky Way, to the ecliptic, or to any local structure. When you look above or below the Sun in any reference frame, at sufficiently large scales, you are looking into the cosmic web. Filaments cross your line of sight. Voids open up. Galaxy clusters glow with the combined light of thousands of galaxies. The directions that seemed empty at solar system scales, the directions the flat diagram deleted, are teeming with structure at cosmic scales. The North Galactic Pole direction, in particular, has been extensively surveyed because it offers the clearest view out of the Milky Way. Astronomers have mapped millions of galaxies in that direction. The Sloan Digital Sky Survey, one of the most comprehensive galaxy surveys ever conducted, concentrated much of its effort at high galactic latitudes, building 3-dimensional maps of the cosmic web by measuring the distances to galaxies scattered across the sky above and below the galactic disk. These maps reveal filaments of galaxies hundreds of millions of light-years long, walls of galaxies forming sheet-like structures, and voids hundreds of millions of light-years across, containing almost no galaxies at all. Directly above the Sun in galactic terms, if you could see far enough, you would be looking through one of these survey volumes. You would see the cosmic web stretching away from you for billions of light-years, its structure growing fainter and redder with distance, as the expansion of the universe stretches the light from the most distant galaxies toward longer wavelengths. You would see galaxy clusters glowing at various distances, each one a collection of hundreds or thousands of galaxies bound together by gravity and embedded in hot gas visible in X-rays. You would see the largest structures in the observable universe, walls and filaments spanning billions of light years, forming a foam-like architecture that fills all of space. And you would see voids, enormous voids, regions hundreds of millions of light years across where the cosmic web's filaments are absent and galaxies are vanishingly rare. These voids occupy roughly 80% of the universe's volume. They are the dominant feature of the cosmos at the largest scales, and they extend above and below the Sun in every reference frame, because at these scales local orientations become meaningless. The galactic plane, the ecliptic, the Sun's rotational axis, none of them matter to the cosmic web. Its structure was set by quantum fluctuations in the first fraction of a second after the Big Bang, amplified by gravity over billions of years into the filaments and voids we observe today. The web has its own geometry, and that geometry has nothing to do with the solar system's flat diagram. And there is one more layer, the most distant one of all. If you keep looking directly above the Sun, in any reference frame, past the heliosphere, past the Oort Cloud, past the local bubble, past the galactic halo, past the satellite galaxies and the dark matter envelope, past the local group and the cosmic web, and the most distant galaxy clusters your telescopes can detect, you eventually reach something that is not a galaxy, and not a void, and not a filament. You reach the cosmic microwave background, the oldest light in the universe. Approximately 380,000 years after the Big Bang, the universe cooled enough for the first atoms to form. Before that moment, space was filled with a fog of free electrons that scattered light in every direction, making the universe opaque. No photon could travel far without bouncing off a charged particle. Then the electrons combined with protons to create neutral hydrogen, and suddenly the fog cleared. Light was free to travel. The first photons that escaped in that moment have been travelling through space ever since, for over 13.8 billion years, stretched by the expansion of the universe from their original white-hot glow to the faint microwave radiation we detect today at a temperature of roughly 2.7 degrees above absolute zero. This radiation comes from every direction in space. It has no preferred plane, it does not align with the ecliptic, or with the galactic disk, or with the cosmic web. It is the most perfectly uniform background in all of observational science, varying by only a few hundred thousandths of a degree from one direction to another. Those tiny variations, mapped by spacecraft like the Planck satellite with extraordinary precision, encode the density fluctuations that eventually grew into every galaxy, every cluster, every void, and every filament in the universe we see today. The cosmic microwave background is the blueprint of all cosmic structure, frozen in light, arriving from every direction simultaneously. When you look directly above the Sun, you are looking toward this wall of ancient light. The photons arriving from that direction have been travelling ever since that first moment of transparency, crossing the entire observable universe, passing through voids and filaments and galaxy clusters along the way, to reach you from a direction that the flat diagram treated as empty. The same is true if you look directly below, or to either side. The cosmic microwave background surrounds us in every direction, including the directions the diagram erased. This is the final answer to the question of what lies above and below the Sun. At the very end of the line, past every structure we have explored, there is the afterglow of creation itself. The directions that the flat diagram deleted as unimportant, the vertical directions, the ones with no planets and no asteroids and no exciting orbital mechanics to draw, those are the directions where, if you look far enough, you eventually see the origin of everything. The beginning of the universe is directly above the Sun. It is directly below the Sun. It is in every direction at once, because the Big Bang was not an explosion at a point in space. It was the expansion of all space simultaneously. The cosmic microwave background is the most distant wall in every direction, and it makes no distinction between above and below, between ecliptic and galactic, between any reference frame any observer could ever choose. The flat diagram erased the vertical directions because they seemed empty, but they are not empty. They lead, through every nested structure we have explored, outward to the oldest observable light in the cosmos. The directions the diagram ignored are the directions where the universe reveals its full depth, its full age, and its full indifference to every local flaw we try to impose on it. This is the final collapse of the flat picture. The diagram on the classroom wall showed you planets orbiting a star in a clean plane. It implied, without ever saying so, that the interesting things in the universe are arranged horizontally, along the ecliptic, stretched out left to right. Above and below were empty, irrelevant, not worth drawing. But we have now followed those erased directions outward through layer after layer of structure. The heliosphere, shaped differently above the sun's poles than along the equator. The Oort Cloud, spherical, extending equally above and below. The local bubble, stretched vertically, opening into a chimney above and below the galactic disk. The galactic thin disk, the thick disk, the stellar halo with its globular clusters, the Fermi and Rosetta bubbles, enormous structures of energy towering over the galactic center, satellite galaxies orbiting through the halo, the dark matter envelope spherical and immense, the local group three-dimensionally distributed, the Lania supercluster, and finally the cosmic web itself, filling all of space in every direction without preference for any local plane. Each of these layers has real vertical structure. Each one occupies the directions that the flat diagram erased, and each one is tilted or rotated relative to the others. The ecliptic is tilted 7 degrees from the sun's equator. The ecliptic is tilted 60 degrees from the galactic plane. The galactic plane has no particular alignment with the local group or with Lania or with the cosmic web. Each layer of structure exists in its own orientation, its own geometry, its own version of above and below. The sun is embedded not in a single flat plane, but in a series of nested structures, each one tilted relative to the last, like a set of picture frames hung at different angles on the same wall. This is the truth that the simple question was always leading toward. What is above the sun? The answer depends on which plane you choose. And no matter which plane you choose, the answer is not nothing. Above the sun, in every reference frame, real structure exists. The directions perpendicular to any chosen plane lead somewhere, through layers of increasing scale, into three-dimensional architecture that the flat picture never hinted at. And here is where the deeper realization arrives. The flat diagram did not merely oversimplify, it distorted our intuition about where we are. It taught generations of people to imagine the sun at the center of a clean, flat, two-dimensional system floating in vaguely empty space. The sun in the middle, the planets around it, nothing above, nothing below. A picture so familiar and so frequently repeated that it became the default mental model for an entire civilization's understanding of its cosmic position. But the sun is not at the center of a flat picture. It is one point suspended in a three-dimensional stack of structures that extend in every direction, including the two that every diagram deletes. The heliosphere is three-dimensional. The Oort Cloud is three-dimensional. The local bubble is three-dimensional and vertically elongated. The galaxy has a disk, but it also has a halo, bubbles, satellites, and a dark matter envelope that together form a roughly spherical system far larger than the disk. The local group is three-dimensional. The supercluster is three-dimensional. The cosmic web is three-dimensional. At every scale, the sun is embedded in structure that extends above and below, and at every scale, the flat diagram failed to show it. The most disorienting part is the tilts. If all these structures shared the same plane, you could at least draw a single updated flat diagram and call it complete. But they do not. The sun's equator is tilted from the ecliptic. The ecliptic is tilted from the galactic plane. The galactic plane has no alignment with the cosmic web. Each structure has its own orientation. The direction called above shifts as you zoom out, rotating through 60 degrees when you move from the solar system frame to the galactic frame, and becoming meaningless altogether when you reach the scale of the cosmic web, where no direction is preferred over any other. The sun is not sitting on a floor. It is floating in a three-dimensional lattice of nested structures, each one oriented differently, each one extending above and below in its own terms. There is no single vertical axis. There is no universal ceiling. There is no ultimate direction called up. Every version of above is local, defined by a particular structure at a particular scale, and every version leads to a different destination. This is what makes the original question so much stranger than it sounds. What is above the sun seems like it should have a simple answer. Point up. Describe what is there. But point up relative to what? The ecliptic? The sun's spin axis? The galactic plane? Each choice gives a different answer, and none of them is more correct than the others. All of them are physically meaningful. All of them point at real structure, and all of them are valid simultaneously. You are living inside a cosmic geometry that no flat picture can represent. The sun occupies a single point in space, but that point is the intersection of multiple planes, multiple axes, multiple definitions of vertical, each one belonging to a different layer of the universe's architecture. The ecliptic defines one vertical. The galactic plane defines another, rotated 60 degrees away. The cosmic web defines none at all, treating every direction equally. And the sun sits at the junction of all of these frames, embedded in all of them at once, belonging to all of them, and centered in none. The flat diagram was never meant to deceive. It was meant to show you orbits, and it does that well, but it had a side effect that no one intended. It flattened your intuition. It trained your brain to imagine the cosmos as a surface, a map, a floor plan with the sun in the middle and nothing interesting overhead. It deleted the third dimension from your mental model of the universe and replaced it with blankness. And that blankness persisted, unchallenged, because no one ever told you to look up. Now you have looked up. You have followed the erased directions outward from the sun through every layer of structure the universe contains, and what you found was not emptiness. It was not blankness. It was not the vague nothing that the diagram implied. What you found was the actual three-dimensional architecture of the cosmos, layered, nested, tilted, and vast. A chimney of hot gas venting from the galactic disk, ancient star clusters older than the Earth orbiting high above the plane, enormous bubbles of gamma-ray energy inflated by the galaxy's central black hole, dwarf galaxies slowly being devoured as they spiral through the halo, a dark matter scaffold extending hundreds of thousands of light-years in every direction. The cosmic web stretching to the edge of the observable universe with no regard for any local flaw. All of it was always there. All of it was always directly above and below the sun. The only thing missing was the question. The next time you see that familiar flat diagram, the one with the sun in the middle and the planets stretched out in a neat line, try something. Imagine looking at it from the side. Edge on. See how thin it is. See how the entire solar system, all its planets, all its asteroids, all its comets and moons, fits into a sliver so thin it nearly vanishes. Now imagine looking straight down at that sliver from above. You are looking along the direction the diagram never shows you. And from that angle, the solar system is not a grand panorama of orbiting worlds. It is a line, a scratch, a faint mark on a vast, deep, three-dimensional canvas that extends above and below for billions of light-years. That canvas is the real universe. The flat diagram was always just a cross-section, a single slice, through an infinitely deeper reality. Directly above the sun, directly below it, in every frame and at every scale, the universe has structure, geometry, and depth that no two-dimensional picture can capture. The simplest question you can ask about the sun, which direction is up, turns out to be a key that unlocks the entire three-dimensional architecture of the cosmos. And the fact that most people never think to turn that key is perhaps the most extraordinary thing of all. The universe was never flat. We just drew it that way.